Okay, scholars, today we're going to start kind of putting some math to all this. Of course, we already have math to calculate the equilibrium constant K when we have two products and two reactants. The main pattern of the equilibrium constant, of course, is this. Reactants of products raised to their stoichiometric coefficient divided by the concentrations of reactants raised to their stoichiometric coefficient if our reaction is like this. And again, this is just a pattern. And you guys know that if we're not at equilibrium, if these are not equilibrium concentrations, then this is not equal to K, but rather some other changeable number called Q, the reaction quotient. We know that all systems in a closed system will reach equilibrium at some point. And we know that usually for a lot of reactions, we end up with a reaction mixture, a significant mixture of reactants and products mixed together at the end. So what if you were given like an initial amount of A and B, and you were asked to find the final amounts of chemical substances. Now this looks a lot like a question that I could have asked you at the very beginning of this whole course. In the past, we just used simple stoichiometry to do this. We would set up a mole ratio and do our conversion, our table ladder conversion, very simply, and we would be able to, we may have to ask, which one is the limiting reactant or something like that. But we would just be using mole ratios, mole relationships, because whenever we did stoichiometry before, we always assumed that the reaction went to completion. We always assumed that all the reactants turned into products. But now it's different because we know that systems are reversible. We're going to end up with a reaction mixture of reactants and products. So because of that, we cannot use simple stoichiometry. We need a new problem-solving strategy. So what we're doing today, once again, is we are solving for amounts in equilibrium systems. And you guys need to know that to do this, we cannot use simple stoichiometry because reactions now, we are saying, do not go to completion. We end up with a mixture of reactants and products. And we want to know how much reactant, how much product we end up with. What is that reaction mixture like? To do that, we're going to have to use a different problem-solving strategy. And the problem-solving strategy that we are going to use is known as an ICE table. An ICE table is used to calculate amounts. Just like stoichiometry helped us calculate amounts for reactions in which all the reactants become products, ICE tables will help us calculate the amounts in chemical equilibrium systems. Systems that are reversible, where we end up with a reaction of mixture, a mixture of reactants and products. An ICE table basically looks like this. You're going to set up a table, and the I stands for initial, and that's going to give you a spot to write all of your initial quantities. The C stands for change. That is where you're going to be able to write what change takes place in your substances. And the E stands for equilibrium, which is where you're going to write an expression for what you have once the system has reached equilibrium. Okay, from this problem-solving strategy, you will be able to solve lots of different things. The only way for me to teach this to you is to do several examples. That's all we're doing today is examples with ICE tables so we can calculate amounts in these equilibrium systems. Now I said that we're not going to use stoichiometry. It's not pure stoichiometry. We're still going to use some stoichiometry, some mole ratios using the coefficients in the balanced chemical equation. That will still be important, but it's just not the whole story. All right, so let's get started with some examples. So here's an example. First of all, I want to write the equation. I have carbon monoxide reacting with steam. These are both gases. It's important for me to note the phase of matter because you know that only gases and aqueous solutions end up mattering for equilibrium. Solids and liquids do not. Okay, this is going to produce carbon dioxide, CO2 gas, and H2 gas. And it looks like this reaction, this collision, I've just swapped an oxygen over here. So this is already balanced, I believe. Let's think about what the question tells us that we know. It says at 700 Kelvin. Does that matter? It's not going to matter for my problem solving right now, but it does matter because they give me the equilibrium constant of 5.10. So my K value is 5.10. That's always tied to a specific temperature, right? So that's why they're telling me the temperature in this problem. So I want to calculate the equilibrium concentrations. So I want to know, what do I end up with at equilibrium? The equilibrium concentrations. What are the actual concentrations I end up with at equilibrium for all of these things? If initially I put all species, every one of these chemicals, every single one of them, not just reactants but products as well, if I put all of them present in 1 molar amounts, mixed in a 1 liter flask. So here's how this is going to go. I'm going to set up an ice table. It's going to just correspond with my reaction system, my equation, I, C, E. And this is going to allow me to organize my knowns and my unknowns for all of these chemical species, all of these substances. Just like that. Okay, and in the ice table, I want to fill in remember what the I stands for? I is initial, C is change, E is equilibrium. I want to fill this in terms of concentrations. I'm dealing with concentrations. Remember, equilibrium is all about concentration. In fact, I could actually pause and maybe first it would be helpful for me to write down what this K actually means, what it's equal to. Remember that this is a ratio, the concentration at equilibrium of my products raised to their stoichiometric coefficient, 1 and 1, divided by the equilibrium concentrations here, CO and H2O, of reactants raised to their stoichiometric coefficients. This is an equilibrium constant. These values must be the equilibrium values. That's what I'm trying to find down here. That's what the question asks me. Calculate the equilibrium concentrations. Well, I know that when I perform this mathematical operation, that whenever I divide this ratio out, it's got to be equal to 5.1. That's what I know right now. So I have 1, 2, 3, 4 unknowns. And so this is going to be a little bit tricky for me to figure out what these concentrations actually are. All I know right now is that they end up at equilibrium making this ratio of 5.1. That's what the meaning of the equilibrium constant. So I'm always going to have to write down my equilibrium constant there, okay? All right. So first I just want to follow this table down. I want to think about what I have initially before the system reaches equilibrium. I know that initially I have taken 1 mole of everything and I've mixed them in a 1 liter flask. And remember, I'm trying to write down initial concentrations, okay? Initial concentrations. Well, concentration is moles per liter. So if I take 1 mole of CO and put it in a 1 liter flask, my concentration is 1 molar, 1 mole per liter. And in fact, that's going to be true for all of these. And really, I should be writing out all these sig figs. I get 4 sig figs because of those decimals, but we can worry about that at the end. Okay, so that is my initial concentration for all of them. The system is going to change in some way. Either the forward reaction will occur to consume reactants and make products, or the reverse reaction will occur to consume products and make reactants. I don't know yet what's going to happen. I don't know yet whether this system will proceed. I know for sure it's going to proceed to reach equilibrium. But I don't know which way it's going to have to go to do that. I don't know if it's going to go forward to make more product, go backwards to make more reactant. So I really cannot talk about the change that takes place yet. I don't know what kind of change happens to my reactants. Do they experience a positive change? If they experience a positive change, that means they get created, and therefore my products would have to be consumed. Or maybe the opposite is true. Maybe my reactants will get consumed, and my products will get created. Does that make sense? So the change is a way for me to talk about the change that happens to these initial amounts. Are the initial amounts of my reactants going to go up, and the initial amounts of my products going to go down because the reverse reaction was favored? Or is the opposite the case? Well, what can I do to figure that out? What I need to do is recognize that initially I'm not at equilibrium. So I could take the time to calculate a Q value for this, a Q value for these initial amounts. And remember, Q is the exact same equation, but we're just not necessarily at equilibrium. So my Q is going to be equal to the concentration of CO2, that's a 1, times 1 over 1 times 1 is the concentration of CO2 times the concentration of H2 divided by the concentration of the reactants. So my Q right now is 1. Typically, the second thing you're going to do to solve these problems, the first thing is always going to be filling out the initial row, figuring out what do you have before the reaction gets going. The second thing you have to do, we need to figure out if the reaction is proceeding in the forward direction or the reverse direction. In order to determine that, we have got to compare Q to K. So I need to calculate what Q is. I've just determined that my Q is 1. Compare that to K. Right now my Q is less than K. I really hope you guys have picked up on this already. If you've not, if you're still confused, you need to go back and watch the previous videos or ask me questions. For a Q less than K, that means that this value is too small. My K value needs to end up being 5.1. That's when I've reached equilibrium, when this ratio reaches 5.1. Right now my ratio is just 1. That's too small. What is the system going to do to bring Q up to K? Q is going to have to, so here's Q, here's K. Q is going to have to rise until it matches K. What can I do to the system? What will the system do on its own to cause that to happen? How can I make this bigger? Yeah, I've got to increase the top or decrease the bottom, don't I? This needs to go up, this needs to go down. The top are my products, the bottom are my reactants. I've just determined, therefore, that the forward reaction is going to occur most significantly now. This system will shift to the right. The system will shift to the right because I have too few products. My Q value is too small, okay? So that's always going to be the second thing you do in these is to think very quickly, and usually you may even be able to do it in your head. Like I could have done this Q in my head. I could have said, okay, 1 times 1 divided by 1 times 1. Oh, my Q is 1. That's less than K. I know the system will shift to the right. The forward reaction will proceed. So because I have just determined that the forward reaction will proceed significantly, I am able to now fill out the change part of my table. In a forward reaction, what kind of change do the reactants experience? Yeah, they experience a negative change, don't they? They get consumed. So I know that these are going to go down, and I know that these are going to go up. My reactants are getting consumed, my products are getting produced because I am indeed favoring right now the forward reaction. My system has to shift to the right because Q is less than K. Okay. This is now where stoichiometry is going to come in to play. The change that these substances experience are all proportional. by the stoichiometric coefficient in your balanced chemical reaction. In other words, think about this. The stoichiometry says these are all related by a ratio of 1 to 1 to 1 to 1. That means that whenever 1 mole of CO gets consumed, the exact same amount of H2O gets consumed, and the exact same amount, 1 to 1, of CO2 gets produced, and the exact same amount, 1 to 1, of H2 gets produced. So I have got to think about stoichiometry. I have got to think about mole ratios for this part of the problem. The issue is, guys, I'm trying to figure out what is left over once equilibrium has been reached, once my Q actually becomes K. I want to know what these concentrations are. I don't know what the change is going to be. All I know right now is that it's negative and that it's all the same because of the 1 to 1 to 1 to 1 mole ratio. So that is my unknown variable X. And by relating all of these stoichiometrically, 1 to 1 to 1 to 1, I can use the same variable. For every X that CO gets consumed, the same value X of H2O will get consumed because of the 1 to 1 ratio. And the same value X, 1 to 1, will get produced here and here. So that is what the change is. You're always going to think about two things. First of all, you have to figure out what the sign is, negative or positive. Which way will the reaction proceed? Will it consume reactants and make products, or vice versa? And the way you do that is a quick comparison of Q to K. In this case, Q was less than K, so I know the reaction progresses to the right. The forward reaction occurs more significantly. My reactants get consumed, so they experience a negative change. The products get produced, they experience a positive change. And I know the second thing I have to do is think about the mole ratios, 1 to 1 to 1 to 1, so they all experience the same change, negative X and positive X. Okay? All right. So then step 3 is to put all of this together to create a statement showing what you have left over at equilibrium. At equilibrium, I'm going to have my initial plus my change, 1 minus X. I started with 1. In order to reach equilibrium, the system has to shift to the right. It has to progress to the right. The forward reaction is favored right now. And so I'm going to get some of that initial CO consumed away. 1 minus X. 1 minus X for water, for steam. And then my CO2 and my H2, those are getting produced. So they're going to experience a positive change. So the initial amount, all I'm doing is I'm taking the initial amount and adjusting it by the change I just thought through. Just like that. Okay? And now what I need to do is actually solve, because this is what I'm after. I want to know what are these equilibrium concentrations. That is what I'm trying to solve for. Well, I need to figure out what X is. If I can figure out what X is, then I'm going to get the equilibrium concentrations I want. Well, how in the world can I solve for X? I need some kind of equation. Well, wait a second. Don't I know how all of these are related to each other at equilibrium? Yeah, they have got to fit in this ratio and they have to equal K, don't they? So down here, once I've fleshed out my table, I'm now going to go to a K expression, the one I have already thought through, and I do recommend this be one of the first things you do so you can refer to it. I have to go there and start plugging these things in and solving for X. Let me make some more space for us real quick to do this. So I know that K is 5.1. And I know that is the equilibrium expression, the equilibrium constant for this reaction. And I know that it's the equilibrium concentrations of products divided by the equilibrium concentrations of reactants. But right here I have expressions for what those equilibrium concentrations are. So the equilibrium concentration of CO2 is 1 plus X. The equilibrium concentration of H2 is 1 plus X. Divided by, I'm just following this equation, recognizing that these call for equilibrium concentrations, and I have those in my table right now. 1 minus x is the equilibrium concentration of CO. 1 minus x is the equilibrium concentration of H2O. And now I have one equation with one unknown. I can solve for this. This is going to get a little bit tricky to solve for. You're going to have some really sharp algebra skills. I mean, I think it's pretty basic algebra skills, but I know you guys may be out of practice for your algebra. So if I was going to solve this, I think that I would maybe I would maybe FOIL the right side first. So I'm going to FOIL the top. So you guys all remember FOIL, right? First, outer, inner, last. That's going to get me 1 plus 2x plus x squared, just like that. 1 times 1 is 1. X plus x is 2x, x squared. I'm going to FOIL the bottom. 1 times 1 is 1. Minus 2x plus x squared. So there I've FOILed both of those, just like that. And I know that that's equal to 5.10. All right. So now I can take this and I can just start rearranging to try to solve. I want to try to solve for x here. So why don't I bring this side up, multiply both sides by this. And when I do that, it looks like I'm going to get 1 plus 2x plus x squared equals 5.10 minus 10.2x plus 5.10x squared. I just need to combine my terms now, so let's do that. I combine my terms and I get 0 equals 4.10, subtracted 1 from both sides. I'm going to subtract 2x from both sides, so minus 12.2x. I'm going to subtract x squared from both sides, so I get 4.10 x squared there. And you guys should all know how to solve this. We're trying to solve for x right now, so that I can plug it back in here and find those equilibrium concentrations. That's the whole point of this question. So you have two strategies right now to solve this quadratic. This is a quadratic equation. I could rearrange it and use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Or you can use your graphing calculator, where you literally just graph this. You graph y equals all of this stuff, and then you find the 0. You find where it intercepts the or the x-axis. You find the x-intercepts where y equals 0. I'm assuming you guys are competent in these two ways of solving the quadratic equation. Whether or not you're actually going to have to solve a quadratic equation on the exam, I don't know if they're going to throw that at you. I mean, they want you to use these math skills to solve a chemistry problem, so it's likely. Later we'll see that there are simpler types of questions where you don't have to use the quadratic formula. Sometimes this gets really complicated when you do an ICE table. You end up with x cubed and stuff like that, and pretty much the only solution you have is use your graphing calculator. So whatever method you want to do, if you choose to use the quadratic formula, of course, you're going to have to rearrange this. We always, for the quadratic formula, we always put the largest terms of x first. So really I should rearrange this to say 4.1 x squared minus 12.2x plus 4.1, and you guys all know that this is 4.1 is the A, 12.2 is the B, 4.1 here is the C. So that's how that works. I'm going to give you guys some time now. I'm not going to belabor this algebra because, once again, I'm assuming you all have the skills. If you don't have the skills, you need to come talk to me. But you should try one of these ways and see if you can solve for x right now. Okay, so you guys know about quadratics that typically you'll get two answers. Here are my two answers. clearly this one has got to be correct because I'm subtracting an X away up here. I cannot end with a negative concentration. I can't end with a negative amount of a chemical. So I'm not going to use this one. I got to use this one. So I've just discovered what X is. Now notice that is not what I'm really after here. I'm not after just the change. That's what X is right now. I am after the actual equilibrium concentrations. So what I need to do is go in and perform all of these operations with the X value I just found. And my X is 0.386. I did that both ways, the quadratic and graphing, and I got the same answer, so I'm confident in that answer. So 1 minus 0.386 here is 0.614, 614 rather, 0.614. 1 plus X, of course, will be 1.386, 1.386. And there it is, your very first ICE table to solve equilibria concentrations. Oh my God, they grow up so quickly. These are my answers, y'all. At equilibrium, I have just discovered that the concentration of CO will be 0.614 molar, moles per liter, moles per liter, moles per liter, moles per liter. Don't forget your units. Now, I could, if I wanted to, take the time to check my work. I could plug all these numbers into this and make sure I get 5.1. You're more than welcome to do that. 1.386 times 1.386, those are my equilibrium concentrations of my products, divided by 0.614, equilibrium concentration of CO, equilibrium concentration of H2, and we do indeed get 5.1. So we know our answer is correct. So let's review one more time what we did. The very first thing you want to do, make sure you have a balanced chemical equation. Second thing you want to do is make sure you know how to write your K expression. Third thing, you need to predict the sign of the change. Remember how we did that? We had to compare Q to K. I took my initial concentrations here and I calculated a Q value with them, same formula as K. And I saw that Q was smaller than K, and therefore I know that the system is going to have to proceed forward or right. So my reactants will go down, they'll get consumed, my products will get created. And then I wrote the initial plus or minus any change that occurs, and then that finally allowed me to create my equation. And then from there, it's just algebra. If you get a quadratic, you have two ways of solving the quadratic formula or graphing calculator. And then you have to make sure that if you get two solutions, find the one that makes sense, find the one that will not give you a negative number, and actually plug it in and solve. So these are my answers I was after. And then if you want to, you can go back and check your work, make sure that the K expression actually does equal your K. And that's how ICE tables work. Remember that for change, the stoichiometry does matter. The fact that these were all 1 to 1 to 1 to 1 meant that they all experienced the same change value of X. So that's the only time we need to think about the stoichiometry. All right, whew. I know that's a lot, but you guys will get the hang of this with practice, I hope. So let's keep practicing. Okay, here's my second example problem. At a certain temperature, the synthesis of hydrogen fluoride gas has this equilibrium constant. 3 moles of each component was added to a 1.5 liter flask. Calculate the equilibrium concentration of all species. Okay, this is just like the last one. So the synthesis of hydrogen fluoride, I need to write an equation for that. Well, I know that synthesis is two things coming together, hydrogen gas, fluorine gas, making 2 moles of hydrogen fluoride, just like that. All right, and I'm going to set up my ICE table. What are my initial concentrations? Remember, we're always speaking the language of concentration in here. Well, I know that initially I put 3 moles into a 1.5 liter flask. Concentration is moles per liter, so 3 divided by 1.5 is clearly 2 molar. So I start with an initial concentration of 2 moles per liter of each of these, of all of them. I make a reaction mixture of reactants and products. So that was simple. Now we want to know whether the change will be positive or negative. So do you guys remember what we have to do to figure that out? Yeah, we have to compare Q to K. So real quick, let me write a K expression. I know that K is 1.15 times 10 to the second. They told me that right here. I know that's equal to the product concentration raised to its stoichiometric coefficient divided by the reactant concentrations. And I know that the formula for Q is exactly the same. So I can solve Q. It's going to be 2 squared divided by 2 times 2, which is clearly 1. This K value is very big, right? That's like 100. So because right now Q is less than K, I have determined that the system will shift and proceed to the right. The forward reaction is happening. It's dominating right now. Therefore, I know that I'm going to have negative changes here, positive changes here. Okay? So we wrote down our initials, 3 moles in a 1.5 liter flask, moles per liter gets us concentration of 2. We did a quick Q calculation to figure out how Q compared to K. We saw that Q was less than K. We need to bring Q back up to K by increasing the amount of products. So clearly the forward reaction will occur. The system is going to shift to the right, or the reaction will progress to the right. So now I need to figure out what to plug in here. It's a little bit more complicated this time because I don't have a 1 to 1 to 1 ratio. This time I have a 1 to 1 to 2 ratio. Remember that in the change portion of your ICE table is where you're going to be worried about these coefficients. You're going to be worried about the stoichiometry. Not too complicated. You're just going to bring the coefficients straight down and use those in front of your X, in front of your change. In other words, for every 1 mole of H2 that's consumed, and for every 1 mole of F2 that's consumed, I get twice as much hydrogen fluoride because it's a 1 to 2 ratio. So the simplest thing to do here is just to bring these stoichiometric coefficients, the mole ratios in your balanced chemical equations, straight down and slap them in front of your X, plus 2X right here. For every 1 of these that gets consumed, I also consume 1 of these, but I produce 2 of these. So this one has double the change. It has a change that is twice as large as these changes, okay? And then equilibrium will be 2 minus X, 2 minus X, and then of course 2 plus 2X, just like that. And I'm almost done. I'm after these equilibrium concentrations. I want to know what these values are. So I got to find that X. I need to figure out what the change is. To do that, I need to plug everything into this equilibrium expression right here. 1.15 times 10 to the second is just 115. So I'm going to simplify that. Equals 2 plus 2x squared. Do not forget that you still have to square it because this is the equilibrium concentration of HF. And because there's a 2 right here, my K expression has that squared. So even though we did have to think about that for the change, we do still have to think about it for plugging it into the equilibrium expression. Divided by 2 minus x, the HF equilibrium, the H2 equilibrium concentration, raised to the first power times 2 minus x, just like that. And then do whatever algebra you need to do to solve it. I'm going to go ahead and factor both of these, the top and the bottom. So that's going to get me 4 plus 8x plus 4x squared down on the top. I just FOILed that. 2 times 2 is 4. 2 times 2x is 4x, plus 2 times 2x is another 4x, gets me 8x. 2x squared is, of course, 4x squared. You guys can actually, write that out if you need to. Do this FOIL. 2 times 2 is 4. 2 times negative x is negative 2x, which gives me negative 4x, plus x squared. Just like that. Now, I suppose that we could pause and see if there's a way for us to simplify this right here, but I don't see any apparent way to do that. Once again, I'm just trying to mathematically manipulate this however I can. Well, I know that all this is equal to 115. And actually, if you're very comfortable with your calculator skills, you can stop right here and plug this into a y equals in your calculator, and then have your calculator calculate where y equals 115. For what x value does y equal 115? You can do that. That is, if you're really comfortable with your graphing calculator skills, you can do that. If you are not, maybe you want to get this in a simpler way, combine all your like terms. So I'm going to multiply this over here. And so the whole thing is going to become 4 plus 8x plus 4x squared equals 115 times 4 is 460 minus 460x plus 115x squared. Combine like terms. That's a 2. So let's see. I'm going to try to get this equal to 0 because it has to equal 0 for the quadratic formula to work, right? So I'm going to subtract 4 away from both sides. That's going to get me 456. Subtract 8 away from both sides. That's going to get me negative 468x. Subtract 4x squared from both sides. That's going to get me 111x squared. Here's now the simplest way of writing this equation. I need to solve for the x values. Of course, you can rearrange it, use your quadratic formula. You can use your graphing calculator. I'm going to do both of those real quick. You guys need to practice the algebra. This algebra should be second nature to you. So when I do this, I get two values for x. I get that x equals 1.53 and that x equals 2.68. Which one am I going to pick? I want to pick the one that actually makes sense. I have to subtract an x away from 2 minus x here. I cannot have a negative concentration. I can't have a negative amount of a chemical. So I need to pick this one right here, 1.53. So I know that my x is 1.53, and now I'm just going to plug that into each of these and solve for those, because that is what I'm trying to solve for, the equilibrium concentrations of these chemicals. When you do that, just some real quick, simple algebra. I get 0.47 moles per liter of H2, 0.47 moles per liter of F2, and 2 plus 2x here for this one. I get 5.06 molar right there. And of course, if we really wanted to, we could plug these back into this and make sure that we do get 115. And I indeed do get 115. All right, so once again, ice table steps. Write out your K expression because you'll need it for later. Make sure you have a balanced chemical equation. Fill out the initial portion. Fill out the change portion. Figure out if your changes are positive or negative by comparing Q to K. Flesh out the X values here by using stoichiometry. There's a 2 right here, so I know that this experiences double the change, twice as big of a change as these do. Combine the initial and the change to create your expression for the equilibrium concentration. Plug these equilibrium concentrations into your K expression, which I did right here, and then just use whatever algebra you need to solve for the X, and then plug it back in to find your final answer, those equilibrium concentrations. Okay? So I hope you understand what's happening. If we start with this reaction mixture, these actual amounts, we've just determined that the reaction is going to progress to the right until it reaches equilibrium, and we have found the actual final concentrations, the final amounts of these at equilibrium, have we not? So that's why this is so useful. It allows you to predict precisely what a chemical system is going to do. All right? Okay, looks like we have 3 more examples. I'm going to try to do these a little bit more quickly. All right, looks like this next one uses equilibrium pressures. And that's totally fine. We can use pressures of gases, right, in our equilibrium expression. It's just a little bit different. But as long as the volume is not changing, the temperature is not changing, then pressure corresponds to number of moles. Pressure is proportional to number of moles of a gas. As long as everything is held constant, volume and temperature. Looks like the volume and temperature are being held constant here. So I can certainly use pressures to solve this. So first thing I want to do is get my equation. Gaseous hydrogen iodide is synthesized. So I want the synthesis of this. Obviously, synthesis is making something from its parts. So hydrogen gas, iodine gas, to form 2 moles of HI, kind of similar to my last one. I'm going to go ahead and write a K expression. This time it's pressures. So this is going to be the pressure of HI, the pressure of my product, squared, divided by the pressure of H2 raised to the first power, times the pressure of I2 raised to the first power. All right. They tell me that initially, they give me the initial pressures here. This problem is going to work pretty much just like the last one. I just wanted to remind you that we can indeed use pressures to calculate. Let's see. Initially, I have HI present in 5 times 10 to the negative first atmospheres of pressure. H2 is present at 1 times 10 to the negative second, and I2 is present at 5 times 10 to the negative third atmospheres of pressure. I want to know what are the equilibrium pressures of all the species, all the chemicals. So remember what I have to do first. I need to figure out if my change is going to be positive or negative for the reactants or products. So I got to figure out a Q value. So my Q value, I'm just going to use this exact same equation. It's going to be 5 times 10 to the negative first squared divided by 1 times 10 to the negative second, the pressure of H2, times 5 times 10 to the negative third, the pressure of I2. And when I do that, all right, when I do that, I get a really big Q value. I get a Q of 5,000. Let me double check that I've done my math correctly. And I indeed have. So this is interesting. This time it looks like my Q value, here's my K value. It looks like my Q value is much greater than K. So what's going to happen when your Q is too big? When my Q is too big, that means that this number up here is too big and this number down here is too small. So I need to reverse that. I need to decrease the product, increase the reactants. I'm going to forward the reverse reaction. In other words, the system is going to proceed to the left. So this time in this example, I'm glad that we're doing this, I've just discovered, and this is why this step is so important that you compare Q to K. I've just discovered that the system is going to proceed to the left, consuming the product. So unlike the last 2 examples where we made product, now my product is going to decrease. I've got to consume product and make reactant because the left reaction is dominating now. And then I think about stoichiometry. For every one of these that gets produced, one of these gets produced, but 2 of these get consumed, just like that. And then we're pretty much good to go. I just have to write my equilibrium expression. 1 times 10 to the negative second plus x. 5 times 10 to the negative third plus x. 5 times 10 to the negative first minus 2x. Those are my equilibrium concentrations. Those are what I'm trying to find. I got to solve for x, so I'll just plug these into this k expression that I've already written. That's why I suggest you write your k expression first. And of course we're given k. It's 1 times 10 to the second, which is just 100. 100 equals the equilibrium concentration of HI raised to the second power, so 5 times 10 to the negative first minus 2x squared over each of these multiplied together and raised to their stoichiometric coefficient of 1. Okay, and now we can try to simplify this out. These scientific notation terms are a little bit difficult for me to think through. So I wonder if really quickly it'd be easier if we just change them to standard. It's totally up to you. 5 times 10 to the negative first is 0.5. 1 times 10 to the negative second is 0.01. It's totally up to you, whatever you're comfortable with doing. 5 times 10 to the negative third is 0.005. Just like that. And of course, when I square something, I'm just multiplying it by itself. So I can just FOIL that. And I'm going to get 0.25 minus 0.5 times 2x is 0.5 times negative 2x is negative x. So I get negative 2x plus 4x squared is me foiling that. And then FOIL the bottom, of course, 0.01 times 0.05. Isn't just watching someone do virtual algebra so invigorating? Don't you guys feel so excited right now? Man, I wish I had this when I was in school. I'm kind of jealous. All right, 5 times 10 to the negative fifth. 1, 2, 3, 4, yeah. Plus, so I'm just foiling first, outer, inner, last. 0.01x plus 0.005x gives me 0.015x, and then of course I'm getting x squared, and I know that all of this equals 100. So here I have several options. I can collect my terms and set it equal to 0 to use the quadratic formula. I can collect my terms, set it equal to 0, use my graphing calculator. Those are probably the smartest moves. I'm not going to take the time to hold your hand and walk you through the algebra. You guys should know that to collect your terms, I just need it to be in the form, to use the quadratic formula, 0 equals ax squared plus bx plus c. And so I need it to look like that. So I would multiply this whole thing over, multiply it there, and then subtract, and then get it to look like this. Anyway, when you do that, you end up getting that 0. You end up getting 0 equals negative 0.245 plus 3.5x plus 96x squared. So there's your A, there's your B, there's your C, and you can plug those into the quadratic formula. When you do that, you should get that x is equal to 3.55 times 10 to the negative second atmospheres. And now I can plug that x in here and solve for the equilibrium, not concentrations this time, but pressures. When you do that, you get that the equilibrium pressure of H2, again, we found the x here. I just want to plug that value in right here. And we're going to get, what is that, 4.55 times 10 to the negative second atmospheres of pressure. The pressure of I2, perform this calculation. 4.05 times 10 to the negative second atmospheres, and the pressure of HI. Perform this calculation, and you get 4.29 times 10 to the negative first atmospheres. And these are my final answers. Okay, so two things were different in this problem. Whenever we compared Q to K, we got a Q bigger than K, so the reaction had to proceed to the left. So we were performing the reverse reaction where we were consuming product and forming reactant. And then the second thing that was different was that we were using pressures, but it really doesn't matter because they gave us the pressures and they asked us to find the pressures, and pressure, as long as temperature and a volume stay constant, pressure is proportional to moles, which is proportional to concentration. So we can do the exact same analysis. And they gave us the Kp value also, the equilibrium constant in terms of pressure. All right, let's keep going. All right, so we have gaseous NaOCl decomposing to form gaseous nitrogen monoxide and chlorine gas, Cl2. So it looks like I'm going to need a 2 here and a 2 here to balance this. There's my K value. And fill out my ice table. Initially, I have 1 mole of reactant NaOCl being placed in a 2-liter flask, moles per liter. My initial concentration of NaOCl, let me change color, is 0.5 moles per liter. And that's all I have. I don't have any of this or any of this. So I know right away that the reaction is going to proceed to the right because I don't have any product, right? My Q, in other words, right now is 0 because it has products on the top. So my Q is definitely less than K. 0 is less than any positive value. So I know that the reaction will proceed to the right. So I'm going to lose reactant, create product, and think about your X values. For every 1 chlorine I make, I'm going to be making twice as much NO, and I'm going to be consuming twice as much NaOCl. You just bring those coefficients straight down. So I get this equilibrium expression, 0.5 minus 2x. 0 plus 2x is just 2x, and then 0 plus x is just x. Of course, I have my K value right here. I know that that is equal to the concentrations of reactants raised to their stoichiometric coefficient, concentration of products divided by concentration of reactants raised to its stoichiometric coefficient. And then I can plug and chug and solve. Just plug in these for each of these. So when I do that, I'm going to get a 1.6 times 10 to the negative 5th equals the concentration of NO squared. So that's going to be 2x squared the whole thing times the concentration of Cl divided by this 0.5 minus 2x, and I'm going to have to square that. And oh boy, you can see that this is going to get really messy really fast because I now have a power of 3 in my problem. 2x squared is 4x squared. 2x, the whole thing is squared, is 4x squared. Times x gets me 4x cubed. I have a cubic function. That's going to be a real pain in the butt to solve. Of course, we can solve for it. Why don't we go ahead and solve for it? I think that might be helpful. And then I'll show you an easy way, a shortcut we can take. Although you should not cheat and you should not take shortcuts in life. So I'm going to go ahead and factor this out. So all this is going to become 1.6 times 10 to the negative 5th. That's my K value equals 4x cubed. I'm just going to factor out the bottom. 0.5 minus 2x, that whole thing squared. Doing FOIL in my head, 0.25. I think I did one just like this earlier. Minus 2x plus 4x squared. And so now we have several options for solving this. We could graph y equals this, graph y equals this and see where the intersection is in our calculator. We can combine all my terms, set it equal to 0, and see where the 0 point is in my calculator. All right, so choose one of those strategies, 4x to the power of 3, I'm going to do this in my graphing calculator, divided by the whole bottom, in parentheses, 0.25 minus 2x plus 4x squared. And then in my other y equals, I'm going to put 1.6 to the power of negative 5. And I'm going to see where these intersect each other. Okay. Anyway, when I plug this into my calculator and one y equals, plug this in and another y equals, and find where they intersect after all that zooming in, because this is really tiny, I end up getting that x equals 0.00974. That was a big pain in the butt. I don't want to have to do that. This cubic thing freaks me out. So what I notice with this question is that this k value is really tiny. It's really, really small. So 1.6 times 10 to the negative fifth. That's 0.123416. That is like 1/100,000th almost. So that's incredibly tiny. What do you guys know is the meaning of a really tiny k value? That means that the forward process is not favored at all. The forward reaction hardly occurs to any significant extent. So listen very carefully. This is going to be true if and only if your k value is very small. If and only if your k value is less than 1 times 10 to the negative 3, so less than 1/1000th. This is a safe thing for you to do. If your exponent on your k value is -2, you really shouldn't do it. If it's some big number, like 5 times 10 to the negative 3, you really are not safe to do it. But if your k value is to the negative 4th, to the negative 5th, like I am here, I can approximate away an x value. I can approximate some x to be equal to 0. Okay? So here's what I mean by that. I start this process with a significant amount of NaCl, 0.5 molar. Does that make sense? Well, because my k value is really tiny, I can approximate right here. You're not going to do this step. You're not going to do this step, what I'm telling you, until the equilibrium row of your ICE table. I can say that because the x value is so tiny, that 0.5 minus 2x might as well equal 0.5. In other words, this thing does not experience much of a change really at all. Okay? It does change, but because my k value is so small, whatever change it has is tiny compared to the actual value itself. So I am safe to approximate that x value away. I do not want to approximate these x values away because I want to know actually what they ended up with, like what their equilibrium concentrations were. Okay? So this helps to simplify my, my expression greatly. If I do that, let's see what my new equilibrium expression would be. I'm going to adjust this. I'm going to keep this old x value just so I can remind myself. This was the x value right here. This was the x value finding it the correct way, I guess. And now let's see what my x value is when I cheat a little bit. So again, I don't want to approximate away this change because the change from 0 here needs to be actually significant. So the concentration of NO is going to be 2x squared times x. I'm still going to have 4x cubed on the top, 2x squared right here times x. And then on the bottom, I'm just going to have the equilibrium concentration of NaCl, which I've approximated to be 0.5 because the change is so tiny, because the k value is so tiny. And that's pretty much just going to be 0.5 squared. And now you can see how simple this is. I don't need to use my graphing calculator to graph anything. I just need to rearrange this and solve for x. So I can bring this up, multiply both sides, divide both sides by 4, and then just take the cube root, right? Raise both sides to the power of 1/3. So x is going to equal 1 times 10 to the negative 6 raised to the 1/3 power. I just raised both sides to the 1/3, which is the same thing as taking the cube root. And when I do that, I get that x is equal to 0.01. So there's my x that I found when I cheated. And that's so stinking close to this one, it might as well be the real value. This rounds very beautifully up to 0.01. So my actual x value is 0.01. Okay? So now that I have actually found my x, remember the whole point of this is to figure out what these equilibrium concentrations actually are. This rounding thing I did right here, and again I did it because I recognize this change of negative 2x compared to 0.5 is really tiny, so as to be insignificant, I can approximate it away. I did that because my k value is really small. Now though, whenever I have done that trick to find what my x is, my approximated rounded x value, I want to no longer hold on to the approximation. I actually want to use this to figure out what the equilibrium concentration of NaCl is. Does that make sense? So I'm done with this approximation now. Now that I have an x, I do want to plug it in to this. Okay, so I'm going to say then that my equilibrium concentration of NO is going to be 2x, so that's going to be 0.02. My equilibrium concentration of Cl2 is going to be equal to x itself, which is 0.01. And my equilibrium concentration of NaCl is going to be 0.5 minus 2x, 0.5 minus 0.02, 0.5 minus 2x, and that gives me 0.48. And so those are my equilibrium concentrations. So let me remind you what we did. First of all, we did it the normal way, just like always, and that was annoying because it got us a cubic function, and then we had to go in our calculator, and it was annoying to solve for. But then we recognized that, hey, because my k value is really tiny, because it is less than 1/1000th, my k value here is less than 1/1000th, I can approximate away the change that my reactant here is experiencing. I don't want to approximate away this because I actually need these in my equation. I approximated away this change, and I said that, hey, this might as well just be, this might as well just be 0.5. It might as well not have changed because the change is so tiny. And then that allowed me to create a simpler equilibrium expression and solve for an approximated x value. This is a fair move on the AP exam, by the way. If you do have a small k value, you can do this. If and only if your k value is small. And so once I had that, I came in here and I undid the approximation, actually had this equilibrium concentration plugged in x just like always into this, into this, into this, and got my overall equilibrium concentrations. Now to check our work, of course, we can plug all this in to this and make sure that we really do get the k. That's always a great way to check your work if you have time for it. So that would be 0.02 squared times 0.01 divided by 0.48 squared. And I get like 1.7 times 10 to the negative fifth, but that is such a tiny little error compared to this small value that it might as well be right. So my approximation was good. So you can only approximate that like that when your k value is small, and you can only approximate the change away from the thing that is present in largest quantities. I did not approximate away this x. 0 plus 2x is still significant here. 0.5 minus 2x, that 2x was not significant, so that's why I rounded that to become 0.5. All right, let's do one more. Nitrogen, hydrogen, and ammonia are all in equilibrium at a certain temperature described by these conditions. So they're at equilibrium. I start with equilibrium. These are in equilibrium. And then I cause a change to the system. I inject suddenly some extra nitrogen gas into the system. So I brought my system out of equilibrium. I want to know what's going to happen. What are my new concentrations going to be when the system reaches equilibrium again? Well, first let's write an equation. N2 plus 3H2 will yield 2NH3. These are all gases, so they all show in my equilibrium expression. My equilibrium expression K is, of course, going to be the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2 raised to the third power. Notice in this problem they don't give us the K value, but we can calculate it because these values are equilibrium values. Because initially the thing is at equilibrium. So I'm anticipating that I'm probably going to need to know what the K equilibrium constant for this reaction is. So I'm going to go ahead and solve this. 0.202 squared divided by 0.399 times H2 cubed, 1.197 cubed. So I'm just plugging these numbers into my equilibrium expression. We've done this about 1 trillion times earlier in this course. And I get a K value of 0.0596. Kind of small, but not small enough, unfortunately, for me to use the rounding trick that we just talked about. Okay, yeah, that K value is not quite small enough. So here's what happened. I suddenly injected some extra reactant. You guys know from the Chatelier's principle that putting excess reactant will cause the system to shift to the right and make more product. I want to know, once it re-equilibrates, once it reaches equilibrium again, what will the new concentrations be? So I'm going to do an ICE table. And my initial values, do not be fooled here, these values were for the system at equilibrium. I just brought the system away from equilibrium by changing the N2 by adding some to it. So my initial N2 is not 0.399. I mean, that's like an old initial state, but I'm curious about what happened after I formed a new initial state, after I added the 1. So the initial value of N2 there should be 1.399. Okay, because that's the concentration that I have now initially when I start my analysis. I have not changed H2 or NH3, so 1.197 and 0.202. We've already thought that the system, we've added excess reactant, so the system has got to shift to the right to make more product. So I'm going to consume reactant and form product. 1 to 3 to 2, so minus x minus 3x plus 2x. For every 1 nitrogen that gets consumed, 3 hydrogens get consumed and 2 ammonia get produced. And then equilibrium here is going to be 1.399 minus x, 1.197 minus 3x, and 0.202 plus 2x. I have, so notice that I kind of quickly did a Q and K comparison. I know that it was at equilibrium. I added excess reactant, which is on the bottom. So I just brought Q too low. My Q has swung lower than K. So to raise it again, the system has shifted to the right. So that's how I thought about the negative, negative, positive there. Same thing as Le Chatelier's principle, right? So I just got to plug and chug. I know what my K value is equal to. Remember, I had to calculate that. They didn't give it to me, but these are all equilibrium concentrations. So I was able to actually plug those in and solve for my K value. And I know that this is unchangeable, right? That cannot change unless I change the temperature. I'm at one specific constant temperature. So I'm going to say that 0.0596 is equal to the equilibrium concentration of NH3 squared divided by the equilibrium concentration of N2 times the equilibrium concentration of H2 to the third power. And this is a really complicated equation. I'm going to have, if you see this, I'm going to have an x to the fourth down here. So I can't use the quadratic formula. I pretty much have no other choice but to use my graphing calculator. Here's what I would do if I were you. I would, well, two things. I would graph this in one y equals, graph this in another y equals, and then find, go to calc, and then intersect to find where those two functions intersect each other. You can do that. Or your second option is to subtract this over so that you get this. 0 equals, plug this whole thing into the y equals, and then go to calc and 0 to see where, at what x equals 0. These are pretty much the only two strategies you have to solve this big monstrosity. It would be really nice if I could have approximated away one of these changes, but my x value is too, or excuse me, my k value is too big. Remember, it's only for really tiny k values that I can do that. So you guys try to do that. Use your calculator skills. Don't forget that parentheses are your friend. So I'm choosing this strategy just because I like to find zeros instead. So here's exactly what I did in my calculator. I went to y1 and I typed in parentheses 0.202 plus 2x close parentheses squared divided by double parentheses 1.399 minus x, so there's one term, times 1.197 minus 3x cubed close parentheses, so that gets me this whole portion, minus 0.0596. That's exactly what I typed in my calculator. I hope you guys can see why I had to use double parentheses here. Okay, and then I'm going to just graph that bad boy. My window is probably going to be all wonky, so I'm going to have to change my zoom, play around with that. And it looks like my function has a 0 way over close to the origin. So I'm going to go to calc 0. I've got to scoot the little cursor to the right, to the left of the 0, to the right of the 0. And when we do that, we get that our x value is equal to 0.0505. So there's your x. And then you can plug that in to each of these and find your equilibrium concentrations. And I'm going to do that now. So I got my new equilibrium concentrations. I found my x value down here. And just like always, we plugged it in to our expressions for the equilibrium concentrations. If you guys need calculator help, please let me know. Remember, whenever you go to solve your homework problems in the packet, I think the first pages of the packet are ICE problems for you to do. You can only approximate away a change when your k value is really small. We can work some of those out together. We'll do that in class tomorrow. This is my final answer. Indeed, the system did have to shift to the right. The amount of NH3 grew, these shrunk. To check our work, of course, we can plug it back into the k expression and make sure that we get the same answer. I always like to take the time to do that. And I do get the same thing. Yay. Alright guys, so I guess maybe now it would be helpful to give you like a problem solving strategy for ICE tables. First, make sure you have a balanced chemical equation. Second, make sure that you've written your k expression. Make sure that you take the time to write that out for your equation. Of course, this is just a pattern that I'm writing now. Write that out. Set up your ICE table. Fill in the initial values. Oops. Think about whether the change will be is positive or negative. To do that, you're going to have to compare Q to K. You guys should be familiar with that, or you can think about Le Chatelier's principle. You're going to complete the ice table. Don't forget that you have to apply mole ratios for the change row. That's like the plus x minus 2x thing, depending on what your balanced chemical equation is, what those stoichiometric coefficients are. Use stoichiometry for that. Write expressions for the equilibrium. An example might be what we did earlier, where your initial concentration minus maybe your change was 2x or something like that. That's going to be an equilibrium expression, something like that, right? And then you're going to actually solve for x using your equilibrium constant K and the expressions for E in your table, what we just wrote right up here in our ice table. Solve for x, and then you're going to use the x that you find to actually calculate those equilibrium concentrations. And then, of course, you can always check your work. Remember that you can approximate change as 0 for some substances in your ice table. Go back and look at that example that I did. I only approximated x as 0, approximated away the x for the first substance because I actually had a significant amount of it, and the change was not significant because the K value is so tiny. So we can approximate away the change, approximate away the x, if and only if your K value is like less than 1 times 10 to the negative third, if it's very, very tiny, okay? Don't forget your algebra when you actually solve for x. You know, you can use the quadratic formula, your graphing calculator, whatever you need to do. Okay, so I hope this is helpful. You guys need to start doing some of the ice problems your own dang selves on your homework, and we'll go over some of them together tomorrow. All right, thank you all for your time. See ya.